Okay, so good morning to everyone. So in the last class, we have discussed about the three-level memory organization. Now today we will start the topic of hardware control unit and microprogram control unit. These two things we will discuss first, and if there is a time left, then I will start the discussion of the input-output processor. So let's start for the hardware control unit, the discussion of the hardware control unit. So what is this? Basically, first, before discussing it, we will know what is the control unit. So basically, control unit, we know that it is responsible to generate control signals for any particular instruction. That means any particular instruction, let's say that we know that from instruction register, the instruction is stored and from there the instruction came. So for any particular instruction to generate control signals for that any particular instruction, control unit is responsible for that. So that's why control unit is basically, it is responsible to generate signals for any particular instruction. Each instruction has some control signals, and to generate that, the control unit is basically responsible. Now, a control unit can be implemented basically by the two techniques. So there are two techniques present for basically implementing that. First one is the hardware implementation. Second one is the microprogrammed implementation. These are the two techniques. By implementing this, there are the two techniques present. First one is the hardware implementation. Second one is the microprogrammed implementation. So the hardware control unit is basically implemented as a sequential logic circuit. So sequential logic circuit means that is using AND gate, OR gate, all the universal gates which we have. Using that, we implement the hardware control unit or a finite state machine. Now, sequential logic circuit is basically the universal gates which we have. Using that, we will able to implement the hardware control unit, and another one is the using the finite state machine. Now, finite state machine concept is basically you have read in the automata, computer automata subject. That is what from one state to other state. If the condition is true, that means from this state to this state it can go. But if the condition is false, then from that state to this state it can go. So basically, depending upon some condition, we are saying that depending upon some condition, from one state it will go to the another state. That is the concept of the finite state machine. So if the condition is true, that means this from this state it will go to the other state. That's it. So implementing hardware control unit is implementing using the sequential logic circuit. That is what our AND or not, all the universal gates, or a finite state, that is from state change from one state to another state. By if the condition is true, that means from this state it will go to the other state. So using this two, the hardware control unit can be implemented, and it will generate what we already know, that after for this it will generate a specific sequence of control signals. So that's why this is the hardware control unit. It is says that hardware control unit is implemented as a sequential circuit or a finite state machine that generates a specific sequence of control signals. So that means this will generate any specific sequence. So the sequence of control signals will be maintained. Now, this is the block diagram. So that means the block diagram is what? Here there will be an instruction register present, and it will be connected with the sequential logic circuit. This will be connected with the sequential logic circuit made with the universal gate, and there will be the status signal as input. The status signal will be there as an input, and there is also a clock signal. Now, which status signal is this? This status signal is basically for the instruction. The instruction status signal. So as an input of this sequential logic circuit, the instruction status signal will come, and also a clock signal will be there. It will come to the sequential logic circuit, and this sequential logic circuit will put the output control signals. So the output signals will be the control signals. And this instruction register is what? This instruction register is basically used for instruction status. This instruction register is basically used for the instruction status, to know what is currently the instruction status and what control signals should be generated for that. So this instruction register is basically used for the storing the instruction status currently. What is the status of the instruction? That instruction status currently, and to control the signals, that should be generated. For this reason, this instruction register is used. Now, what it will do? It will fix the logic. So it will fix the logic, and this sequential circuit will do what? It interprets the signal. It will do what? It will fix the logic and interprets the instruction. So the instruction status signal will come to it, and also the clock signal will come to the sequential logic circuit. So sequential logic circuit will do what? It will interpret that. It will interpret that, and after interpreting, it will process that, and after processing, it will generate the corresponding control signals. So as an output, we can see the control signals that is present. So this will do what? It will interpret the instruction and then generates the corresponding control signals. The factors for designing it, the factors we have to keep in mind. That what are the factors we have to keep in mind? The amount of hardware. Now, amount of hardware is always try that minimum hardware is required, because if we choose minimum hardware required, we want that this can be made, this sequential logic circuit can be made with minimum required amount of hardware, so that this sequential logic circuit cannot be very much complex. We want that if we use minimum hardware, then the sequential logic circuit will not be so much complex. So this point should we have to keep in mind, that the amount of hardware should minimum. Then speed of operation. So the speed of the operation should be maintained, that we want the speed, that very much speed this sequential logic circuit works, because we want efficiently to get the output control signals. So that's why the speed of the operation should be maintained. And the third one is the cost. Everything. Now that means what we have to do inside this sequential logic circuit. Now let's say inside this we have one IC present. Now if we use the one IC there, then we will get the output very time bounding, that will be, because only one IC is present there. So instead of that one IC, if we replace this with multiple ICs, then that means what? The multiple instructions will be executed at a time. So multiple instruction status signal will be what? It will be our executed, and we can get the control signals very fast. But it should keep in mind that the cost of that cannot be increased. So cost things also should have to keep in mind. So that's why these things, for designing the sequential logic circuit, we have to take these three things. The amount of the hardware, minimum hardware should be there. Speed of the operation, yes, speed of the operation is also necessary, because we want that multiple instruction status signal will be efficiently executed. So the speed of the operation is very much necessary for us. And also the cost. Yes, we can replace many ICs, but that began that our cost get very increased. It is not good idea. Then what we have to do, we have to keep in mind that the cost should also be reduced. So these three factors are used for the designing purpose, and these three factors should keep in mind. Okay, so now we will see the four techniques, that are used for designing the hardware control unit. The four techniques. First one is the state table method. Now, what is the state table method? The state table method is the classical method of the sequential design. This is what? This is the mainly used method. That's why it is said that the classical method of the sequential design. Between these four techniques are used for design the hardware control unit. And among them, the most common technique is the state table method. This is the most common technique. So that's why it is said that the classical method of the sequential design. So this approach is very much used, classical method of the sequential design. The thing which we already seen, that we required minimize hardware, minimum amount of hardware should be required. So in this method also you see we require minimize hardware. Then the third is construct a state transition table. So what is the state transition table is basically? That means there will be a table present like this, a table will present, and inside this table there will be the source state and there will be the destination state. So from which state to where it is going, from this state to that state it is going. So this information will be stored into that table. So let's say we have like this, from A state to B, from then C. So these are the three states we have, A, B, C. So inside this, upon consuming what, like say 001, that is what, like say 01 it is consuming, and after consuming the state transit from A to B. So this information should be maintained inside this state transition table, and that thing should be constructed. This state table method use this. So construct a state transition table is used in the state table method. The name you see, the name suggests that state table method. That means a state table should be maintained. That's why it is said construct a state transition table. These things are used. And the last thing which is used by this method, this is the every generation of the states has a set of control signals. Now this state, let's say there are the three states. So this state has also a set of control signals. This state has also a control signals. This state has also a control signals. So every generation of the state has the set of control signals. So each and every state has some control signals present. So this is basically the state table method does, and these are the thing which state table method does. That is, it minimizes the hardware, construct a state transition table, and every generation of the state has some control signals. Okay, so these are the first technique, that the state table method. Now the second technique is what? The delay element method. Now why this second technique came? So the second technique came basically for the state table method. You see, we have said that every generation of the state has some set of control signals. But you think that each and every time the control signal should be in the proper sequence? It may not be possible, because let's say from transition from this state to that state, let's say from transition to A state to, we can say, like if we see, like from A state, this is the A state, from B state, from transition it take like 2 milliseconds or 2 nanoseconds. that is millisecond or nanosecond. What do you think? But from B to C, it takes 4 nanoseconds. It may happen some from state transition, some from some state to that state, it takes some amount of time, and from that state to another state it can take much more time. So the proper sequence cannot be maintained for this. It may happen some state consume very fast, some state consume that very less, so it may happen. It depends upon. So proper sequence, sometime, let's say this take 2 millisecond or nanosecond, that takes 4 nanosecond. It can happen because proper maintenance should not be present there. It may happen. So that means what? We can say delay occurred. So to improve or to difficult this, we can say this difference, for this difference or to improve this disadvantage, the delay element method is used. Now inside this delay element method, control signals follow the proper sequence. So from transition from each to any state, same amount of time should be required. So that's why it followed a proper sequence. And that's why you see, it is said a specific time delay, a specific time delay between the two groups of control signals. So we know that each and every state, we already see in the state table method that each and every state generates the control signal. So that means what? This control signal, the specific time delay, that means if this state take 2 millisecond or nanosecond time from transition from this to here, then from this to here the control signals, because each and every state will generate control signals. So that means it will, this changing will also be 2 millisecond or nanosecond. That was why it is said the proper sequence is maintained. So the specific time delay between the two groups of control signal, because this state will generate a group of control signals, this state will also generate a group of control signals. So between them the time delay is what? 2 milliseconds. Then this state also generates some control signals. So from this and this, between these two also there is 2 milliseconds. So that is why we are saying that the specific time delay between the two groups of control signals. And to maintain this synchronization, to maintain this synchronization, the D flip-flop are controlled by the common clock signal. So that's why the clock is basically used. So clock is basically used for that. If the clock is done, that means this clock signals in the first clock, it will move from this state to that state. So let's say if we take this example, from A state to B state, the transition will go. Then in next clock pulse, from B to C, the next, from B to C, the transition will be done. So that's why basically to ensure this, we use the D flip-flop. But in this D flip-flop, we have to use the clock signal. The clock signals is very necessary because one clock signal, it will change the state. So to ensure this synchronization, we uses the D flip-flop, but this D flip-flop will be controlled by the common clock signal. Okay, till now it is clear to everyone? समझ में आया सबको अभी तक?
Yes, sir.
Okay, so this is the second method. Now the third and fourth method which we have, it is not very commonly used, but for knowing purpose, know that sequence counter method. Now counter, it is basically used that if you know, that is what we, the counter in digital electronics, you have read that the counter is there, ripple counter. So from shifting, the shifting should be occurred. For that wise, the sequence counter method is used. So it is used to counter for the timing purpose. And the PLA method, This is what it is, the programmable logic array. These two methods are used. One is the sequence counter method. Now it uses the counter for timing purpose, and the PLA method, it is used for the programmable logic array. So these are the two methods we use. So this is all about our hardware control unit. Okay, now we have already seen we have two types there. We have two types. One is hardware control unit, one is the microprogram control unit. So the hardware control unit is basically this. Now we will move to see the microprogram control unit. Now you can say that hardware control unit is basically what? The approach of the hardware, you see, based on the sequential logic circuit, or based on the our finite state machine, it will generate the control signals. So that means based on that sequential logic circuit or the finite state machine. But the microprogram control unit, the name says, that means here the programmable approach will done. You see, microprogram control unit, its name is. So that means it will be implemented using the programming approach. But in that case, for the hardware control unit, it is based on the hardware approach. The hardware approach it is based on. But the microprogram control unit is basically based on the programming approach. Now here, what we do, we have a sequence of micro operations. We have a sequence of micro operations that are carried out by executing a program consist of micro instruction. Now basically what it says, that the microprogram, a microprogram consists of micro instruction. So inside the microprogram, there micro instructions are present, and inside the micro instruction, the micro operations are present. So that means if micro operations is executed, then what we say, a sequence of micro operation, because inside the microprogram the micro instruction is there, and inside the micro instruction micro operations are there. So if a sequence of micro operations are carried out, that means to perform the sequence of micro operation, what we have to do, we have to execute the microprogram which consists of micro instruction. That is said that executing that micro operations, we have to execute a program consist of micro instruction, because either we cannot able to do that. So the sequence of the micro operations are carried out by executing a program consist of micro instruction. And that is what it is said, that inside the microprogram micro instruction is there, and inside the micro instruction the micro operations are there. So for sequence of micro operations, the sequence of micro operations executing, we have to execute the microprogram which consists of micro operation. That is what it says. Okay, so this is what the concept is. Now the microprogram consists of micro instruction stored in the control memory of the control unit. So this microprogram, which is consist of micro operations, are stored in the control memory of the control unit. So the control memory of, or you can say the ROM of that, it is stored in there. So basically the control memory of the control unit, this micro instruction are stored. That means microprogram consists of micro instruction stored in the control memory of the control unit. Means in the control memory of the control unit, the microprogram which is consisting of micro operations are stored. And executing of each micro instruction is responsible for generating the set of control signals. So here the execution of the micro instruction, it is responsible for the generation of the set of control signals. Okay, so it is basically this micro instruction is basically responsible, but there we have seen that from state to state change, the each and every state is responsible. That is what it is said, that every generation of the states has the set of control signals, because they are the states are able, the states are responsible for that. But here the execution of the micro instruction, because it is following the programming approach, it is follows. So that's why the execution of the micro instruction is what it is responsible for generation of the set of control signals. Now we will see the architecture of the microprogram control unit. Now the architecture of the microprogram control unit is what? Here you see the first is the next generator address. Now this is connected with the control address register. Then this is connected with the control memory. Then this is connected with the control data register, which there will be the two output. One will be the control word and another output will go as the input for the next. This is the next address information. This output will go as the input of next generator address again, and there will be the external inputs will also be present. So this is like a counter. You see, this is like a counter. So from next generator address, it will be passed to the control address register, then it will be passed to the control memory, and from it will go to the control data register, and it will produce two output. One will be the control word and another output will go as an input of the next address generator again. And this next address generator has what? This is one input and another input is the external inputs. These are the two inputs of the next address generator. Now basically we will know that what it performs. Now this next address generator is what? In this we have the address of the micro instruction. Now inside the micro program there is micro instruction present, and each and every micro instruction has some address, has some sequence of micro instruction, and each one has some address. The address of the micro instruction, the address of this micro instruction that is to be executed, stored into the control address register. That means the micro instruction which we want to execute, that particular micro instruction address, that particular micro instructions address will be stored to the control address register. So here from this next address generator, the address of the micro instructions will go. The particular micro instruction which we want to execute, that particular micro instructions address will be stored into the control address register. This will be stored into the control address register. And the micro instruction, the next micro instruction is what? The micro instruction corresponding to that address. That means this particular micro instructions address will be stored into the control address register, and this control address register will do it fetched from the control memory. So from control memory it will be fetched, and this micro instruction contains the control word to execute one after one or more micro operation. After the execution of the micro operations of all the address of the next micro instruction is located. So the next address informations will be good as the next address information for the next address generator. So there will be the external inputs for the next address, there will be there, and it will go as the micro instruction contains control word to execute one or more micro operation. Okay, so what is the advantage of the this technique, microprogram technique? It is basically less complex. It will be basically less complex to design because microprograms are implemented using the software routine. So it is basically what? It is basically less complex. That is not, it is basically less complex to design because of the microprograms. Here no hardware, not like that hardware is there. Hardware is there, but minimum amount of hardware is there. So it is less complex to design because of this microprograms, and these microprograms are implemented using the software routines. Also, it is more flexible. It is also more flexible. Now, why this is more flexible? Because for designing, modification, correction, because any modification, any correction, any enhancement, or any changes, let's say any changes, if we have to done in the microprogram control unit, then it is very easy. So if it is easy, that means we can say it is very flexible. That time we can say it is very flexible. So that's why it is said it is more flexible, because design of the modification, correction, and enhancement is easily possible here. So that's why it is more flexible. Okay, so the time is very less. So I will request everyone to join for the rejoin the next session, because I will start the new session now. The time is very less. So that's why I will start the session.